Okay, well, good news. Short one today. So I just have to finish up this doing operations and other bases, so subtraction and then multiplication. Spoilers, just like addition, it works exactly the same as the old method, the regular method for base 10, which you have probably long since forgotten, and that's totally okay. But there's nothing fancy about it. You just have to keep track of your conversion rates. But speaking of, that's the topic we started talking about was base conversion. So converting from one base to another base. So the most common computing would be base 2 to base 16, or vice versa. Sometimes octal, or obviously base 2 to base 10 and vice versa. That's something that you would, you don't personally do it with your computer unless you are using bitwise operators, in which case you definitely will do that. So there's lots of bitwise operators that let you operate directly on the bits of variables and stuff like that. So that's why you care about actually understanding base 2. And we talked about how to go back and forth between the bases. I use sort of like a currency example, right? Think of it as denominations of currency. So like the denominations of the bills is what your base is. And you're just making change, or you're ask the bank for money, right? And then we talked about addition, which works exactly the same way as the base 10 algorithm. We just have to exchange at a different rate. So at base 10, when you do like 7 plus 8 and you get 15, you would write down the 5 and carry the 1 because you have 15, right? That's 10. So you exchange the 10 for 1 above and write down the 5. So if you were in base 7, you would exchange 2 and then write down a 1, right? So like that's what we care about when we do these operations, right? It's the exchange rate. That's the only difference. It's just how much do I trade over to the left. And so that's essentially what we're going to do here with subtraction. So again, we're just going to start with an example in another base, because subtraction is just sort of the inverse operation of addition, so they're very, very similar. The only difference is we have to borrow things sometimes. So again, that would be the exchange rate that matters. So let's do So we're going to do 412 minus 124 in base 5. So subtraction here, let's not even pretend we're in base 5. We just work from right to left and just do the subtraction, right? Like 2 minus 4. Now, in the base 10 algorithm, we look at this and we say, well, I can't take away 2 from 4. That's not big enough, right? I mean, I know you could say, look, well, negative numbers, that's not how this algorithm works, right? We say, I want to take 4 away from 2. I can't, so I have to borrow from the next one over, right? So we have to borrow here. So we want to do 2 minus 4, can't, so must borrow from the left. So what we would normally do, so like if we were dealing with base 10, we would cross this out and say, okay, I'm taking one of those away. So you reduce it by 1. And then you would say, this is not 2 anymore, it's 12, right? That's how it would work in base 10. We're not working in base 10, though. We're working in base 5. But the idea is still the same. In base 10, we added 10, which was the base. In base 5, we add 5, which is the base, right? So we borrowed a 5, not a 10. So we're going to cross this out and write 7 instead. So we do 2 plus 5, which we would call the borrow. And then we take away the 4. So that's 7 minus 4. We can do that. That's 3, right? So we go ahead and write down 3. And now that's that part of it, right? We've done that one. And so now we just rinse and repeat, right? We follow the process all the way through. So we look at this, we say, all right, I need to do 0 minus 2. Again, can't do that because 0 isn't big enough to take away 2. So we have to borrow again. So we're going to take this, and now we cross this one out, and we add 5, because 5 is our base. So now we do 5 minus 2, and we get 3. Now we do 3 minus 1. We don't need to do anything here, right? Because that's just the end, right? We would just say 3 minus 1, that's 2, right? So this is, again, if this is even taught anymore, I don't know. I'm 36, so it's been a long time since I was in elementary school, which is genuinely when this algorithm is taught, if it is anymore. So I wouldn't fault you for forgetting this. But the point here is that algorithm works no matter what base you're in, right? It's the same idea. It's just the exchange rate again. We're exchanging 5s instead of 10s. So we could say 4, 1, 2 in base 5. When we take away 1, 2, 4 is 2, 3, 3, right? So let's go ahead and do another example. This one is base 11 because that base, the bigger bases are a little weird just in how we notate things. Right, so base 11 has an extra digit in it compared to base 10. So let's do A01 minus 1A8. So this is the same thing, right? We want to do 1 minus 8. We can't. That's not enough. So we need to borrow. But this is a part of subtraction. We say, okay, I need to borrow from the left. I can't borrow from the left because it's 0. And I can't take anything here. So I have to go over again and borrow so that I can borrow. So what we're doing is we're going to say, I want to take from here. I can't. So I need to take something from here so that I can put something here. And now this is where things are a little weird. There's kind of a couple things you could do. I like to write the word. So I just borrowed 11, so I would write 11. Because if you write that, is that 1, 1 in base 11, or is that the number 11, right? So it's a bit ambiguous, yeah? So that also is fine. I'll accept, I accept that too. The weirdness about that is B is not a digit in base 11, so it's like, technically we know that's probably what we would choose because base 16, that's the natural thing. And then if you went to base 18, we know what we would choose past that, right? We just keep going with the letters. So that's totally fine too. So the suggestion was, can't we just write B? Because we know that in base 16, as an example, it would go 9, A for 10, and B for 11. And that's also fine. That's totally, basically whatever you write, as long as you don't get confused, that's kind of what matters here. And I think the vast majority of students, if you just wrote 11, that's technically incorrect in a mathematical sense, but I don't think you would get confused writing that. I think you write that and you're going to be like, I know it's 11, right? Because like over here, if we did this in base 10, we would write 12, right? And we don't get confused in base 10, right? Because everything's assumed to be base 10 there. So I think it's fine either way. I like to write the words, but like I said, you can write B or whatever symbol you want to represent this. But the point is, we borrowed from here so that now this could be 11, right? Which means now we can borrow from it. So now we cross this out, and this is 10, which we do have a digit for, that's A. And this is another reason why maybe you would want to write B, because then you cross out B to get to A. And now we cross this out, and now it's 11 plus 1, which is 12, right? So now we borrowed from here, finally, to get to here. So it's 12 minus 8, which is 4. And now we can actually do the subtraction. Okay, great. What about here? We don't have to borrow again. It's A minus A, so that's just 0. 9 minus 1, that's 8. Great. So then our final answer is A01 minus in base 11, 1A8 is 804. So the point with this example is sometimes you have to kind of follow a chain of borrowing in subtraction, right? You'll just have to, if you've got a bunch of zeros here, that's just what you have to do, right? You have to borrow. And that's it for subtraction, right? It's basically the base 10 algorithm. It's just, again, the exchange rate's what's different, right? With addition, what you carry, or when you carry, is what changes, right? You exchange 5 for 1 to the left, or 7 for 1 to the left, whatever. What changed here was how much you borrow when you go to the left, right? That's it. So the last thing to talk about is multiplication. So we're not going to talk about division. And the reason why is not that it's like particularly challenging, I would say. It's just cumbersome, because what division is, if you don't know, is repeated subtraction. That's all it is. That's what integer division is. It's just subtract a bunch of times, and then the number on the top of the division algorithm, that's just how many times you subtract it, right? That's all it is. So we could adapt that algorithm here too, right? We could just do repeated subtraction a bunch of times to figure out the answer, but that requires you to be able to do base 12 subtraction in your head, which, I mean, no. I mean, probably you could if you stared at it for long enough, but then, like, at that point, we're not really talking about algorithms anymore. Now at this point, I'm just making you do long division, and I don't think there's a whole lot of point to that. So we're just going to talk about multiplication. Now, the division algorithm is like a good programming question, because you're implementing an algorithm in a computer, and you don't have to worry about doing base 12 subtraction in your head. You just make your computer do it, right? So that can be fun. But for multiplication, because it's a bit more involved, let's talk about the algorithm. So we're going to do, I put my colors in my pocket and then just kind of forgot that they were in there. So we're going to bust out some colors for this. So 7, 4. I think this is how I have it. I accidentally printed in black and white, so that's not super helpful. So, well, that's what I'll go with. So this is the multiplication we're going to do, but in base 10. So this is the normal multiplication algorithm. So what we do here is, I mean, the point of this long multiplication algorithm is that you don't have to write anything down, right? You just kind of do it in your head if you know your times tables from 1 to 9. That's all you need to know for this, which is why it's kind of nice. So this is 4 times 7, so that's 28. So we write 8, carry a 2, and then we do 4 times 3, so that's 12. Add the 2, that's 14. Carry the 1. Write that down, right? What this is saying is 4 times 37 is 148, right? That's what this algorithm is doing. And then in terms of the algorithm, we write a 0 there, and then we're just going to add stuff up, right? And we start over, but using this number now, right? So instead of going 4 times 7 and 4 times 3, we're now going to do 2 times 7 and 2 times 3. So 2 times 7 is 14, carry the 1. 2 times 3, that's 6, plus the 1 is 7. So we add this up, 8, 8, 8. Wow, that's a fun coincidence. So I'm going through this kind of fast again, because this is just how the algorithm is. And the reason why this algorithm exists is because you can do long multiplication for arbitrarily big numbers, right? And all you need to know is 1 to 9 multiplication tables. But what's going on here? So there's a couple pieces that we want to sort of abstract so that we can try to figure out how to do this multiplication in other bases. So the big one here is carrying. So let's go back to this first step here, where we did 4 times 7. Right, so 4 times 7, I'm going to write it in my red. So 4 times 7, that was 28. Right, so when we did that, what we ended up doing was we said, okay, I carried a 2 and I wrote down 8, right? So what really happened is this is 2 copies of 10 plus 8 left over, right? So just like with addition, right, we had an exchange rate. When we were above 10, we had to move stuff to the left, right? We put a number above a carry digit, right? And that's the same thing that's happening here. We have this 10 exchange rate. So we wrote down this number right here. And the number in front of the 10, that was our carry, right? And that's just what we carried over. And then we did the same thing here. We did, okay, 4 times 3. Yeah, let me use green. So 4 times 3 plus the 2 that we carried gave us 14, which was 1 10 with 4 left over. So we write down the leftover, and then we carried the 1. Like that, right? And then it was 4 times, so there's always a 0 there. So it's 4 times 0, we write down the 1, right? And that's really what's happening with this algorithm. So the reason why I'm drawing attention to it is, well, this right here is our exchange rate, right? That's base 10. We are in base 10, so we have a 10 exchange rate. That's the only part that changes in multiplication too. It's the exchange rate again. So it's a little trickier with multiplication just because there's kind of a lot going on here in terms of keeping track of things, right? You have to pay attention to what base you're in a lot more often. So technically it's possible to do in your head, but it gets a little weirder. I would not recommend doing multiplication and other bases in your head. Let me just show you what I mean with another example here. So let's do base 4. So I'm going to write it. I'm going to use my colors like this. I know. Complain more, Travis. It'll make it better. 3, 2. You know what? I'm just going to ruin my shirt. They can go in there open. Times the number 1, 2. And this is base 4. So, okay, so we're going to do this multiplication in base 4 now. So we do the exact same thing. And one thing you'll notice here is in lower bases, the multiplication actually gets easier in a sense, because there's sort of less to keep track of, which actually means base 2 multiplication is pretty straightforward, which is why logic gates can do it very easily. But let's go through the motions here. So this is 2 times 1 is 2. Okay, great. So we just write down 2. Now we move to the next one, 2 times 3. That's 6. Okay, but that's bigger than the base, right? So we need to move some. We need to make an exchange here. So this is 1 copy of 4 plus some stuff left over. So in multiplication, we write down the leftover stuff and we carry the number in front of the base right here. So that's 1, so we carry the 1. And now we rinse and repeat. We say, okay, now I do 2 times 2. With the 1 I carried over, we add it. So this is 5. Same thing now, right? We have 1 copy of 4 with 1 leftover. We write down the leftover, and we have another carry. I don't have enough colors. So we carry the 1, And again, there's always a 0 sort of leading in front there. So 2 times 0 plus 1 is 1. We don't need to do anything fancy there. All right, great. So now we follow our algorithm here. We're going to write a 0 here and move to the next number. So now it's 1 times 1. This one's pretty easy. 1 times 1 is 1. So we don't have to worry about any carries or anything like that, which, speaking of, this is something I'm absolutely terrible at, and I think most people are when they do this algorithm. We should, now that we've moved to the next step, we should erase our carries or cross them out or whatever you want. I tend to forget to do it until I have to make a carry, and then I'm like, oh wait, I left those there, and then I cross them out. But in any case, we're going to write down 1 because we just did 1 times 1. 1 times 3 is 3. And then 1 times 2 is 2. So we write down a 2. All right. Now we're almost home free on this algorithm. But so we have to add these up. And this is the mistake that if students make a mistake on multiplication after doing it like once or twice, this is where they make the mistake. The thing you have to remember, we are working in base 4. So the most common mistake is this is 100% correct. Did the multiplication perfectly. And then they do this addition and do it in base 10. So remember, this is still base 4. So now we've moved to an addition problem in base 4. So remember, base 4. So 2 plus 0 is 2. 2 plus 1, that's 3. 1 plus 3, that's 4. So that's 1 copy of 4 with 0 left over. So we write the leftover and carry a 1, right? Same thing, 1 plus 1 is 2, plus 2 is 4, is 4. So same exact thing. We have 1 with nothing left over. So we write down a 0, carry the 1. 1 plus 0 is 1, like that. Right? So then all told, 2, 3, 1 in base 4. This a little different. Is 1, 0, 0, 3, 2. So multiplying in other bases is the same as base 10. We just have to really, really, really carefully keep track of the base we're working in. So technically, it is not necessary to write any of this stuff on the side. If you could do it in your head, I do not encourage that because it's so easy to make mistakes that, and from the instructor perspective, if you write nothing down, if you just write down your answer and it's wrong, I'm giving you 0 because I don't know what you did. Did you write down a random number? I don't know. I can't tell. You didn't show me anything, right? You just wrote down numbers. So you would at least have to like show your carries and stuff like that, right? Like if you showed your carries, I'd be like, okay, you obviously did some multiplication. I could probably figure out what you did wrong. But that's why, like, if you're not confident in your ability to keep track of this stuff in your head, then it's easy enough to just write it on the side. Because like here, I could do, well, 2 times, and some of it you don't have to write down. Like this one right here, you didn't have to do any carrying. So, 1 times 2 is 2. So you write down a 2. Here you could go, okay, 2 times 3. That's bigger than my base 4. So I'm gonna write it down to figure out how much carrying I have to do. Because sometimes, like in multiplication, this is a small example, but I mean, if you do big enough things, you will have to do big carries. Like over here, if you did 9 times 9, that's 81. So you have to carry an 8 and write down a 1. So sometimes you have big things to carry, so it's important to keep track of that sort of stuff. Okay, so I'm going to write down one more on the board. But we're going to do it my classic way. The Travis Classic. Give me something in base 11. I don't care what it is. At least 2 digits. 832? Sounds great. Works for me. Okay, so let's go through this multiplication. So, exact same idea, right? The base changed, doesn't matter. We do the same thing. So I'm only going to write down the steps now that have carries, but if you're more comfortable writing everything down just to, keep it consistent, go for it. But here we have 2 times 1. We don't need to do anything fancy, right? We just, 2 times 1 is 2. Now this is where things, though, when we're dealing with bases bigger than 10, is where we might need to do some extra thinking. So here we have a times 2. Well, that seems like a weird thing to write, but a represents 10, right? So if you want, you could say this is 10 times 2 is 20, or you could just know that this is 10 times 2 and that's 20. But now we're in base 11, so this is 1 piece of 11 that fits in there, and what do we have left over? We got a 9 left over. Right, that adds up to 20. So, okay, we write down the 9, carry the 1. 2 times 0 with the 1 is just 1. So this is 192. And now we repeat the algorithm. 2 times 0.
Oh.
Yeah, because there's always a 0 there, right? So just as an aside, there's a reason why we do it that way. Why here you see when we do this carry, it's 2 times 2 plus 1. The carry is added because these are place values, right? So if we think of like 37 times 42, this is 2 times 7 is 4, carry the 1. It's because multiplication is repeated addition. So we've just now noticed that 2 times 7 is 14, so we need to capture 10 somehow. So by putting a 1 here, we're actually adding 10, right? That's what this means. We're adding 10 to whatever the result of the multiplication is. So that's why we do it that way. But that's a good remark, so I can sort of mention that in passing. And now we rinse and repeat. I realize I need more space for this. So now we're working with the 3. We're going to want to get rid of our carries. And we rinse and repeat. We say, okay, 3 times 1, awesome. Don't need to do anything, right? It's 3 times 1. Next, we've got 3 times a, or a times 3. Like I said, you could write out what this symbol means, or you could just say, that's 30, right? If you're able to do it in your head, go for it. If you need to say what is that symbol times 3 is 30, whatever you're comfortable with. But now this is 2 times 11 plus 8, right? So now we have 8 left over, so we write the 8, and we carry the 2. Same thing, 3 times 0 plus 2 is 2. Now we rinse and repeat again. We're on to the next digit, so we write 2 zeros now. Cross out our carries, and do it again. 8 times 1 is 8. Awesome. 8 times a, that's a big number. This is 80. So doing multiplication in other bases kind of does need you to know your times tables. If you need a calculator for it, that's fine. But in this case, we need 7 copies of 11, which is 77, with 3 left over. So all I'm doing here is I'm asking myself, how many times does 11 fit into 80 before I would go above 80, right? So, 11, 22, 33, 44, 55, 66, 77. I can't go further than that. So I write down 7 times 11, what's left over? I write down the leftover, carry the 7. 8 times 0 plus 7 is 7. And now we do our addition, which is base 11. We do base 11 addition here. 2 plus 0 plus 0. That one's easy. 9 plus 3. All right, do that on the side. That's 12. So that's 1 copy of 11 with 1 left over. So we write down 1, and we're going to carry a 1. Now, we got some bigger addition happening here. So this is 1 plus 1 is 2, plus 8 is 10, plus 8 is 18. So 1 plus 1 plus 8 plus 8 is 18. Again, is one group of 11. With 7 left over, we write down the leftover and carry our 1. 2 or 1 plus 2 is 3, plus 3 is 6. 7. Oh, is that what you got? Nice. So then all told, A1 times in base 11, 832, which is a random number that you guys gave me, 76712. Just some answer, right? So doing these algorithms, and this is kind of true just in general, not just with math, but I would say in general. And if you're working on something in programming and someone presents you an algorithm, like without you actually getting to do it, you just like read about an algorithm. Sometimes you're like, I have no idea what that was. I that didn't make any sense. But then you actually go to implement it and start playing with it and doing it. And you're like, okay, I understand the pieces now because I am playing with the pieces and they fit together nicely and I get it. Multiplication and other bases is kind of the same thing. You might look at it and you're like, I kind of got lost in the sauce there. And then you start actually doing it and you're like, okay, I get what he's saying when it's just keeping careful track of this exchange rate, right? Once you do that, everything kind of just falls into place and it doesn't matter what the base is. Any questions? All right. Guess what I have for you? Yay! You'll never guess what it's on. Is it math? Well, I mean, that's a pretty broad choice. So what if I told you it was on integration in calculus? Then you would tell me, Travis, go home, and I would be like, that's fair. No, it's on base conversions and all that. I don't even think I have my calculus resources anymore. I would have to like go out of my way to invent a joke calculus problem for you.